Okay, how to count. Now, there are different ways to count, and you have been taught to count in denary decimal. That's base 10, we refer to that. What base 10 means is there are 10 different symbols that we use. We start with 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. So there's 10, the key word is unique symbols. In primary school, you were taught to count your fingers. And unfortunately, people have confused counting your fingers with counting. Is you have 10 fingers, so you count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But that's not how we actually count. When you think about it, we should start counting on 0. If we're going to do this properly, we should close our fists and go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then stop. Because 10 is actually two symbols put together. It's a 1 and a 0. The big thing is counting is about patterns. What you're doing is you are going through a unique combination of symbols. When you get to the end, you've got to the end of that pattern. So there's a big misconception that we actually count from 1 to 10. We don't. It's even gone through to things like the abacus. I was in a famous furniture store that sells cheap products, and I counted the beads on the abacus and realized, hang on, there's 10 beads on this abacus. But it should actually be 9. You slide them all to the left for 0, and as you slide them over, when you get to 9, you then slide them all back to 0 and go down to the row below and start moving a 1 across for 10. So it's so indoctrinated into our idea that we count from 1 to 10 that we find it difficult not to. But actually, we shouldn't. We should count from 0 to 9. Go through the unique symbols, and then we start repeating the pattern. So if you look here, I get to 9. I have now run out of unique combinations. Didn't take long because there's only one symbol shown at a time. So when we run out, what do? We repeat the pattern of 0 to 9, and we add a second symbol. So now we're going 0, 0, 0, 1, 0, 2, so on and so forth, all the way up to 0, 9. Now, at this point, the 9 needs to go back to a 0, and the 0 now kicks over to the next symbol in the sequence, in the pattern, which is a 1. Get to 19. The 9 would go back to a 0, and the 1 would go to the next sequence in the pattern, a 2, 2, 0. Now, because there are 10 symbols, there were, from 0 to 9, there were effectively 10 unique options. So that 1 of the 19 there, that actually means that you've already gone through 10 unique options once. So what 19 means is 10 unique options plus the 9 unique options. 19. 10 plus 9. It's all about patterns. That's what we're actually doing there when we count to 10. Sorry. When we count to 9. It's indoctrinated in me as well. And when we think about what that means then, here I've got 4 zeros. The first 0, on the right-hand side there, highlighted in blue now, well that's, we times whatever that is by 1, because that's our first one. So we have 0 times 1, or if it's 5, that would be with 5 times 1. Sounds obvious, but that's what we do. When we have exhausted those options, we then go to the next symbol. And remember, that symbol means for every time we click through from 0 to 1, and then from 1 to 2, and then from 2 to 3, to the right-hand side, for every one of those 1 clicks on the right-hand side, we have gone through 10 possible combinations, 10 unique symbols. So it is worth, that second one is worth 10 times whatever the one on the right was worth. So 10 times 1. And when we get up to 99, We've run out of unique possible combinations, so we add another symbol, and that 0 kicks over to a 1, and we have 10 times 10. There's 100 possible combinations there. So a 1 means we've already gone through 100 possible combinations. A 2 would be 2 times 10 times 10, 200, and so on for 1,000. When we get to 999, we then kick over, they all go back to 0, they reset their patterns, and the last one kicks in as a 1. We've now gone through 1,000. And it's this idea of there are 10 digits, so we multiply each one of those by 10. Let's do this with a number. So 1,369. Well, the 9 is 9 times 1, because it's the first one, unique combinations. But the 6 is 6 times 10, so it's 6 times 10 plus 9. And the 3 is 3 times 10 times 10, because it's effectively 300. So it's 10 times the combinations before, which in itself was 10 times the combinations before. So, and the 1 is 1 times 10 times 10 times 10. So when we actually write down numbers in denary decimal, we're in fact using a shorthand for something we've assumed. In this case, 9 plus 60 plus 300 plus 1,000. And that's how we count. That's how you should have been taught to count. You would have found it much easier. Computers can't count to 9. They can only think in on or off. Inside a computer are lots of wires. Those wires can either be switched on or they can be switched off. So when we're looking at the combinations you can have, there's 2. 1 for on, 0 for off. And those 1s and 0s, each one of these we call a bit, is literally an actual piece of wire somewhere. Even if it's on the microchip and it's really minute, it's a wire, and that wire either has electricity running through it or it doesn't. It's either switched on or it's switched off. 1 and 0. This is what we call binary. We also call this base 2 because there's only 2 possible combinations. But the method we use to count in binary of repeating, you go 0, 1, you've run out of combinations, so you then add an extra digit, is exactly the same, except instead of it being times 10, it becomes times 2. So let's look at this now with binary. Here, I'm starting with 0, 0. Then the smallest bit goes up the sequence, it becomes a 1. I've now run out of options. 0, 1, that's it. I can't go 2, there is no 2. So my 1 has to go back and repeat the pattern. It goes back to a 0, and therefore, moving along, we have to change the leftmost 0 into a 1. It goes along its own pattern. You'll also notice with this pattern that the smallest bit goes 0, 1, 0, 1. The second smallest bit, it's doubling. It's 0, 0. There's 2 noughts for every 1 0 on the other side. And then 2 1s. It's 0, 0, 1, 1. So the actual way it goes through, it doubles. Here, I've actually got 4 noughts going all the way up to 4 1s. This is, in computing terms, 4 bits or 1 nibble. And you can see me counting this way. So I start with all noughts, then I get my first, my 1. I then have run out of combinations, so the 1 resets to a 0, and the next one along becomes a 1. So we get 0, 0, 1, 0. Well, after 0, on the rightmost, that smallest digit, I've got a space now. So 0 can become 1, so I get 0, 0, 1, 1. We're now at the bottom of the first column. Well, it's like having 99. After you have 99, the next step is that 9's reset to 0, and the next one becomes a 1. You get 100. Well, here, it's not 9's, we don't have those. 1, so 1, 1, those 2 1s both reset to 0, and the next one along becomes a 1. So if you look at the top of the second column, you'll see both of those 1s have reset to 0, and the next 0 along has become a 1. And the pattern keeps repeating that way. And again, if you go through all 4 patterns, you'll see that the smallest bit, as it counts, goes 0, 1, 0, 1, 0, 1, 0, 1. The second smallest bit goes 0, 0, 1, 1, 0, 0, 1, 1. It doubles. The next smallest bit, that's the third one, so or second from the left. So that has 4 noughts and then 4 ones, and then 4 noughts and then 4 ones. And the final one, the largest bit, the biggest number, that goes 8 noughts, so it goes across 2 columns, and then 8 ones. And this is how we count in binary. Let's do the maths list then. So the smallest 0 is just times 1, it's itself. The second smallest 0, well, there's 2 possible combinations, so for every one of those it's times 2. The next one there is worth 2 times 2, and the next one's worth 2 times 2 times 2. And on the right hand side you can see that that means that they're worth 2, they're worth 4, they're worth 8. So each of those digits, as we get bigger, is worth twice the amount that the one before was, rather than 10 times the amount as you're used to. Throw in a bit of mathematics to actually work this out, and we can see that the smallest one there is 1 times 1. The next one is 1 times 2. It's worth twice the one before it. The next one is 0 times 4. Well, it's a 0, so okay, it's going to end up as 0. But if it were to be a 1, that would have been a 1 times 4. Now, that one in blue there you can see is 0 times 4, because that digit is worth 4. And the last digit, the biggest digit, was doubled again, so that's worth 8, so it's 1 times 8. So when we work out what that binary actually means, so you can see on the lines there, 1, 0, 1, 1 is equal to 1 plus 1 times 2 plus 0 times 4 plus 1 times 8, which is 1, 2, 0 and 8 added together, which gives you 11 in base 10. I'll do it a slightly different way. Let's remember, here I've got 5 columns. Each column is a bit, and each column is worth, as it goes across, twice the amount, the one beside it. So the smallest column is just worth 1, the next smallest column is worth 2, the next smallest column is worth 4, then 8 and 16. Let's give it a binary number now. So in the grey is our actual binary number. And we start with the smallest one. That's 1 times 1. The next one is 1 times 2. The middle column, well, that's a 0, so that's 0 times 4. The next one, 1 times 8, and the next one is 1 times 16. So all of those ones, they don't represent ones, they represent the number above, hence 1 times 16. That last one we've got on the left side there is actually worth 16. If we work that out, we get 16 plus 8 plus 0 plus 2 plus 1, which gives us 27. So that number you can see in binary, in the grey, in denary is actually worth 27. Okay. Hopefully you've understood this. There's a quick quiz. Please go through the quiz on the PLE and make sure that you have understood how to convert from base 2 binary to base 10 denary. Thank you.